Hi there, welcome back to the breadboard. This is the second video in a set of two where we review the REYAX RYLR896 LoRa compatible transceiver radio. In this video we're going to review the software. The first video we looked at the hardware and specifications and how we were going to test it. And now we're going to actually look at the software that we implemented and see it working. We have the software running on an Arduino IoT33. It's an Arduino Nano, as you can see in the picture here. We also have it running on a P1AM100 Pro Open microcontroller PLC, which is right there. So as you can see, we've got one module here, the other one's off screen on the bottom right. Let's go back to it. So the software is pretty much identical because the microcontrollers in both of the units that are running this are both a SAM-D21 based microcontroller, and they're both Arduino compatible for their development platforms. I did not find any suitable or worthwhile examples of using the REYAX RYLR896 modules when I went Googling for any. Usually you would find some. All they did was simply have one module being used as a transmitter while the other one was simply being used as a receiver, and they didn't do any real handshaking or pass any viable data or anything else. So what I've done is I've put together my own application where, as you can see here, I have a DHT22 sensor, the IoT33 Arduino, and the REYAX transceiver module. We also have a blue LED, which is just simply putting a status on and off for letting us know when it's receiving messages, etc. We'll also be outputting data on the serial console, serial 1. We use serial 2 to talk to the REYAX RYLR896 module, and serial 1, which is serial 1, I guess. Sorry, serial 0, but you just say serial. And the standard serial port is just used to send messages up to the console. So this is what we would end up with. I'm just going to bring them both up. The one on the right here is the PLC, and it's sending hello there out along with the timestamp using the MILS command in the Arduino. The other one on the left here is the IoT33 Arduino, which is receiving the hello messages and sending back the temperature and humidity. The schedule of both of them is set to 5-second polling at the moment, which is way faster than you really should use for LoRa, as I mentioned in the first video. But in the short time I'm going to be doing this demonstration, it should be fine. And they're running at 2 independent 5-second intervals. Anyway, enough of that. Let's get to the code. Now, a word of warning. The code that I've written is not what I would call beginner code. It is pretty straightforward, but it is a little longer. I've got included in here some additional code for using the DHT11 and various other things, but I just want to go through the code that I'm using right now for the radio modules. So first thing is I've got 2 sets of code here. One is for the PLC that I have one module connected to. The other one is for the Arduino IoT33 module. You'll see that they're almost identical, so I'm not going to spend too much time going through everything in both of them. The one on the left is for the PLC version, and you can see we've got a few setups up here, which is defining a few of the messages, or at least the headers of messages that would be coming in or out of the radio modules. So you can see at the bottom here we've got the AT plus send equals 0, so I'm using network ID 0. We've got the response from most commands, which is plus OK, the header for error messages, the header for a received message from over the air, a delay which I'm using for a loop, so that I only send a message every 5 seconds. That's still way faster than what I'm supposed to, but I'm just using that so that you're not sitting there all day waiting for it to send the next message. And then I've got a parameter here which is used for a loop delay timer that doesn't use the delay command, because that's very wasteful on resources. Okay, same thing is on the other side, only I've got the addition of a library pulled in for the DHT22 temperature sensor. Not going to get into that bit. In the setup, I've got the standard serial begin, setting the baud rates, and I've also got a serial 1 begin. You'll see that's the same for both of these. That's so that I can talk to the radio module and also send out messages through the COM port to my PC so that I can look at what's happening. I've defined a pin mode for the built-in LED on the PLC. It has a user-defined LED that I can flash, and I've got a different LED on the Arduino, which I've used as pin 2, called it blue LED for a constant. And so I define outputs for those. I also define an output for the pin that's connected to the reset of the radio module. I then issue a reset to the radio module because you never know what might have happened to it before you start running your program. So I take the pin low, wait 100 milliseconds and take it high. I have no idea whether 100 milliseconds is long enough or way too long. I just put it in and it seems to be fine with it. I do that on both sides. I start my humidity sensor. On this end, I would normally start a routine for the PLC as well, but that's commented out for now. I have no sensor on the PLC, so I'm just making up a test message when we get to that. Now I've got the main reset here. What I do is, after I set everything up, I do a quick check on the serial port to see if the radio actually has sent anything. That's where I was expecting it to say ready, but I didn't receive anything that said ready. At least I haven't been able to capture it anyway. And then I flash the LED 5 times really quickly just to let me know through a visual indicator that things got past the setup at least. The next thing is the standard Arduino loop, which is where the work really begins. So what I do is, the first thing is I check my millis, which is a counter that's, when the Arduino powers up, it starts at 0 and then just ticks up every millisecond. And I'm comparing it to the send delay plus the last time I sent a message, and if it's exceeded it, then I will drop into this little bit of code. Otherwise I will ignore it and go down outside and flow through, and I keep doing that in the loop. And that's all I'm doing in this loop, is I'll check the time, see how long is elapsed time, and if it's past my expected time, I will call send test data, and then I'll reset my delay loop so that I then skip it again for a certain amount of time, which if you remember was set to 5,000 milliseconds, which is 5 seconds. The other thing that I've added into this is a test for command complete, because there's no real way of polling the radio module to see if it's done transmitting. So what I've done is I know that a plus OK or an error message will be received through the serial port if anything has completed successfully or an error occurred. So I'm using both of those to set the command complete to true, and then when I call send data, I will set it to false, and then it'll sit and skip it until I get an OK. So that way I don't try and send 2 commands over the top of each other or anything silly like that. Because you could overwrite data if you're not careful and you transmit and garble it. And then what I'm doing every single time through the loop, which is probably thousands, hundreds, if not thousands of times a second, is I'm checking for received messages, because they could come at any time. If you had several dozen transmitters all out there sending a message every 100 seconds or every 2 minutes or whatever it might be, then you could get a message anytime. So there's no delay in this. I'm just calling it all the time. The only time that I have a delay is sending my own data. So this is where your send delay would be factored into how long that calculator says your duty cycle should be. So let's look at what receive message does. So in order to talk to these REYAX modules, I'm looking at my serial port and seeing if I've got any data arrived. If I have, then I copy it into a string variable so that I can start looking at it and evaluating what it is. So this is where I have a few if cases. I could probably do this with a case, but I just used if so that more people can understand what I'm doing. So if the message starts with, that means it can have a lot more, and in most of these cases they do, the message receive constant. And if I go back up to the top of the code, see message receive is plus RCV equals. Right? So if plus RCV equals, which is what this is. So if the message starts with that, then I know that I've got a transmission from another module, and I'll call a subroutine called process message. This is keeping my main routine very neat and clean. All right. If it's not that, but it is an error header, so plus ERR, then I'll call process error. And if it isn't that, and it's got just simply a message OK, then I will call message OK routine, right? Process OK message. I don't do anything. The command Boolean that I showed you before is not handled in here because we don't know what else there is there yet. I handled it in the routines further down. If it isn't any of those, then I simply print whatever that message may have been, just to cover anything else that might have come through. And if you look on the other side for the IoT33, it's identical. The next part here, which I'm not going to go into details with, is the send DHT data. This basically just reads the temperature and humidity, and it wraps it up into a string. So I create a string. I know what it is because I've taken my temperature and humidity and I've constrained them to just 4 characters, plus a dot, which makes 5. And then I've got the T equals and H equals as well. So that makes it 5, 10, 11, 12, 13. So there's 13 characters in total in this message, I believe. 4 characters in each. 2 digits, dot, and then a single digit. 2 digits with one order of precision, and then there's a point. So there's 4 and 4, which makes 8, 9, 10, 11, 12. I have a bar separating the temperature and humidity, which make it easy for code processing on the receiving end to break it apart into the separate parameters if I wanted. This is all part of programming design and protocol design. I didn't use any specific kind of protocol here. I wanted to keep the message short and easy to understand. So all I'm doing is saying I'm going to send 13 characters. That's my payload length. It's going to be T equals and then whatever the temperature was, bar H equals and then whatever the humidity is, and then the /rm, which is the carriage return line feed. The carriage return line feed is not counted as part of the payload. So that'll just send the temperature, humidity, and the whole thing is 13 bytes long, and it has a bar to split it, so you can easily pull it apart at the receiving end. There we go. And then I just serial.print the same message that I got so that I can see what's going on in the command console debug. The send command is using send message plus all of this. So send message at the top was that little bit here we had, which was AT plus send equals 0. So there's your address it's sending it to, and comma, and then whatever the rest is that we're adding in. Okay, nice and simple. That's all we're doing for that. And if you look at the PLC side of things, I'm not reading a temperature sensor. I'm just sending test data. Now in this case, my test data is hello there with an exclamation, and then I'm also adding the current milliseconds. So because mils will change over time as the long grows and grows and grows, it'll start off with like 1 character, then 2, then 3, then 4, etc. as the number gets on. I can't have a fixed payload, so what I'm doing is I'm converting the mils to a string, adding it to hello there, and then doing a payload.length plus whatever the payload is plus the carriage return line feed. So this is building the message a little bit more dynamically. I could also have done that over this side, I just didn't for the moment. Then I print my message, and then I send the command, or I call the send command routine. So basically this is equivalent to the send DHT data on the other side. So here are all my functions that I wrote, which are very, very simple, easy to understand, for handling the different types of messages that are going to come out or go in to the radio. So we've got process message. And then I've got, this is when we get a RCV message. So I flash the LED twice in this case, so that I just say, hey, I got a message, ding, ding. And then I just print the message. Now, if you wanted to do something, this could be a message that came from the PLC saying, read your data, or change your frequency of the loop to something else. Or it could be turn a fan on because, hey, your temperature is getting pretty hot, so I want you to turn a fan on to cool things down, right? That message could be anything. But right now, all I'm doing is saying hello there. And it just sends the message. Sorry, this is when I'm receiving a message. That received message coming in. It's the same on the other side, right? Where is it? There, process message. Over this side, I flash the LED 3 times, and then I just print the message. The next one is process any errors. So in this case, of course, I just serial print whatever the error was, and I say I received an error, and there's the error message. And then I set the command complete equals true. Right? When I process the message, I'm not doing anything because this is just a received message. There was no command that I'm waiting for. It's already done. All right? And that could come in while it's still trying to transmit something too, so you don't want to clear the ongoing one. Here we got the process error. I do a command complete equals true. And same on this side. If I get a process OK, so I got an OK back, plus OK back from the radio, I then just print whatever that message was, and it's just going to be the plus OK. And then I also set command complete equals true, which will allow that loop in the main loop where we are checking the delay time and the command complete. It would allow it to go into that little subsection of code again and send another message. So if I get a message to send because the time has run out and I have completed any previous commands, then I come into this routine, I pass the message to it. I print the message, and then I set the command complete to false to say that I'm just starting a new command, and I flash the LED. Now serial1.print is actually sending, I just glossed over that, it's actually sending the message to the radio. It could be a command, or it could be something to change the parameters, or it could be a command to transmit a message. Either way, it says I'm just starting it, so it sets the complete to false, and then it flashes the LED once. And same on this side. And then I've got flash LED is just a utility little function that just takes the number of times to flash, and it just runs through a little loop here just to do that. All right, standard stuff. So that's my two routines that, as you can see, they're pretty much identical. I will do a separate video on how to use a DHT22. It's got nothing to do with the REYAX review, so I'm just not going to do that right now. So what I've got is I've uploaded these to the 2 modules, and I have 2 serial monitors going on right now, right here. So what we have here, the 2 serial consoles. The COM5 one on the left here is the one that is connected to the PLC. So it is sending, if I just stop this from scrolling a second, it is sending AT plus send 20 characters, hello there, and then the milliseconds right there. Right, that's what it keeps sending, and you can see the milliseconds changes every single time because it's just counting up through time. Okay, it's also receiving messages, so there's the OK from the command that it did the send. It's also receiving messages plus RCV, again address 0, 13 bytes, T equals 25.0, yes it's 25 degrees here, and humidity is 55.9%, and I've got a RSSI of minus 40 dBm and a signal to noise ratio of 42. So that's what's happening here, and it's repeatedly getting that from this one, which is sending it. And if I just, it's not so easy to stop this one scrolling, but you can see I'm receiving the hello there with the, get one down here, you can see there with the milliseconds counting up each one, right? They're different for each one. Signal to strength, signal noise ratio, and the RSSI, and there's our message hello there as well. And you can see I'm also sending the, right, one of these, that's the message I'm sending. So AT plus send 0, 13, which is the number of bytes, and then the temperature, and then the humidity. So those are being sent as well. If I put my hand over the humidity sensor, I just go there. So if I just put my hand over this, it's probably going to change its temperature and reading. So if I go back to there, temperature's at 24. Now it's at 26. The humidity's gone up to 71 from 50 odd. Humidity's up to 80. Temperature's up to 26. Yeah, humidity's 86. So I'm creating a lot of humidity on that. So you can see the data really is changing. And it's being sent over right here. There's the 90% humidity now, 26% temperature. So there's a great example then of using a REYAX 950 megahertz RYLR896 transceiver module to be part of a long distance IoT sensor module. I've used a tiny little IoT33, which will work with Wi-Fi and Bluetooth, but the problem with those two things is they're basically stuck to within 30 meters or a bit more, if that, depending on what's around them, range. So if you're going to put this in the middle of a field or at the far end of a factory or even several kilometers away, because of depending on what your implementation is, then Wi-Fi is just not going to cut it if you don't want to put Wi-Fi and other infrastructure in place to get that signal all the way there. But using something like one of these 950 megahertz modules, you can send that temperature and humidity data, in this case, over up to 15-kilometer range. I'm not going to do a range check right here. Plenty of people have done in the past. I will do one in another video, but what I wanted to do right now was have a quick look at these modules, figure out how to use them, and show you how I'm using them. All of the code and the diagrams will be posted on my website so that you can download them. I'll put them on GitHub as well, so you can download it and play with it yourself. The code for the PLC, as I said, is pretty much identical with the exception of a couple of pins to the IoT33. This will also work, as I said, on pretty much any other Arduino module. The difference between the code that I've got now for this and what has been available in the past on the internet, as far as I've been able to find, is that all of those examples using these modules have just had one of them acting as a blind transmitter and not really doing anything, and the other one acting as a blind receiver and not doing anything either. So what I'm showing you here is the fact that I'm dynamically taking data from an actual sensor and sending it over the sub-gigahertz radio waves to a receiver that is then sending it out of a serial port. In a future video, which again becomes not relevant to the REYAX 896 modules, I will show how to hook up an LCD display to print it, or send it over the a Wi-Fi or Ethernet to an HMI module or something, and maybe even integrate it into Node-RED. These are all things that really are not relevant to the transceiver review. So what do I have to say about the transceivers? Well, they were, on reflection now, I would say they're very easy to use. They just work. I will be experimenting and make another video, because this one's probably already way over half an hour, using the modules in faster modes for sending and receiving, and we'll do some actual performance testing with it. But I guess the downside that I found is that there was such a lack of support on how to use these. Now, I guess one thought might be that they try to make it so simple with just the AT command set that anybody could write their own interface logic and code and just get things working. When I was querying it, they said, well, you could just write a routine that acts as an acknowledgement. And what they were meaning by that is that when the receiving module gets a message, it could send back an acknowledgement to the transmitter to say, hey, I got it, everything's good. So you would have to send some kind of message ID as part of that round trip. But if you consider the fact that these modules are only supposed to transmit once in 100 time period wise, then if you've just got your message and sent it, and then you've got to go and do some processing and send that result, you technically would have to wait several minutes before you could send that other response. So you don't really want to have to do that if you don't want to. You want to be able to know when the module has literally finished sending it. And again, as I said, that doesn't mean the receiver's received it. It just means it's gone out over the airwaves. It's basically fire and forget. But then you could expect a response with whatever you ask for. And in this case, I could send a message to say, send me the temperature and humidity, rather than me just doing it automatically every 5 seconds. By sending that back, but also including, say, the mils that was sent as part of the transmit payload, untouched, sending it back again, that would give you a kind of a tie-in to the message that was sent to say, hey, this belongs to that message. And in that case, you could correlate it and say, okay, that message is now done processing. I can move on to something else. And if you were doing a big network of these where you were sending out commands, maybe you were turning things on and off like fans and lights and cooling systems, as well as reading temperature, humidity, and air pressure, or who knows what, then you really would have to have a messaging stack that keeps track of what's been sent and what's been acknowledged and dealt with, rather than just firing and forgetting, because maybe it didn't get received and so the fan didn't get turned on to turn on the cooling, and you'd need to resend that message again to try it again, or raise an error because it wasn't being dealt with. This would take obviously a lot more coding to start implementing something at that level. What I've done here is just show you how you can extend, get the basics working and then extend it to suit your own application. Now, I will be extending this both in the PLC and on the IoT33 to take a cleaner and more full implementation of a remote sensor, and I'll get it working on battery and maybe walk it down to the waterfront, which is several kilometers away from my house, and see if we still start receiving data, which will be quite nice. But that's topic for another video. So what do I think of the modules? I think they're very good. They're not the cheapest modules out there, but they are a good price. Looks like this. Yeah, this is the proper Reyax Amazon, in this case Amazon.ca. Available from these sellers. Well, okay, I found one on eBay. $181, but that's for 10 of them, so basically 18. Yeah, so they're sort of $15 to $18 each. You would need, obviously you'd buy as many as you need. Now the one benefit is it's extremely easy to use. As I've already shown you, $15 is it's already approved. You don't need licensing. It's easy to implement into pretty much any application because it's just serial in, serial out at TTL 3.3 volt levels. So yeah, $15 a piece. That's not really too bad. Yes, you can get ESP 8266s and various other RF modules much cheaper, but they don't have the same kind of range as this. And we already looked at, if we just look at generic LoRa modules, you can see here, here's a LoRa module from SparkFun, 915 megahertz, one channel, using an ESP32, probably as the controller for it, and that's $50. Long range transceiver shield, this one's a 433 megahertz robot shop, which is $24. So yeah, $20, $18, $20 seems like a reasonable price for a LoRa compliant module. I'll provide links in the description. Anyway, I'm going to call it done for this video where we're just going through the use and first impressions of these modules. I do like them. I'm going to probably talk to Reyax about getting some more of them. Could be fun to set a few sensors around and do some longer term testing with it for reliability, etc. for radio waves. And I'm in Canada, so we regularly get minus 20 degrees outside. Right now we're sitting about plus 27 degrees. And yeah, so get rid of that. This was the REYAX RYLR896 transceiver. Next video on these is going to be using them for a long range IoT sensor. So we're going to get more into using the sensors and managing messages and commands and things like that. So it'll be less on the technical aspect of using the radio and more about integrate them into an application, though we will be then getting into obviously range performance checks with it as well. I might separate out the range part of it from the rest of it, just so that if you're interested in range tests rather than what I'm doing with an application, you can just watch that part of it. Anyway, that's it for now. If you like the video, give it a thumbs up. If you don't, well then don't. But I'll provide links to all of the parts that I've used here so that you can go get them yourself. I will also put the code on GitHub and circuit diagrams as well that I used for this particular example, so that you can follow on and implement one yourself if you want to. Bye for now.